I'm Curtis Wong here at Microsoft Research, and I'm really pleased to have Alyssa Goodman here to talk about her work on visualization. Alyssa and I first met about a dozen years ago. There was a Kavli conference in Chicago, um, and she was showing some how you would use brain imaging software to visualize the interstellar clouds, I think something like that. It was 12 years ago. And I had something which was a PowerPoint about this dream thing of how to build a virtual universe and visualize it. And so she came up to me and said, if you ever do that universe thing, I want to help. And that was the beginning of Worldwide Telescope 12 years ago, I think in May. So I'm thrilled to have Alyssa here, and let's kick it off here. I think you're going to find this really interesting.
I hope so.
Yeah.
Anyway, thanks for coming. And so I'm only going to talk about Worldwide Telescope for like 2 minutes later. And instead, I'm going to talk mostly about GLUE and what Curtis mentioned about medical imaging and astronomy intersecting was really just, it was kind of in the state of Worldwide Telescope a dozen years ago. It was just sort of an idea. And now we've had a couple rounds of collaborating with people in the medical world on software approaches, and I'm going to show you our recent and most successful one, which is called GLUE. But before I do that, I should tell you that there's lots more information online, and so here's a whole bunch of links, and I will acknowledge both NASA and now most recently NSF who are funding this project. So the GLUE software that I'll talk about when I get to the specifics is completely open source and a Python program. It's licensed under the MIT license, and so anybody who'd like to use it and make it whatever you want, be our guests. And by the way, are primarily the 4 people listed there. So Chris Beaumont was a graduate student who worked with Tom Robitaille, who's the last person there. Tom Robitaille was a postdoc at the Center for Astrophysics at the time. And Chris learned Python in like 3 days from Tom, who's a Python guru. Chris now works for Netflix. He has a PhD in astrophysics, but we lost him to Netflix in between to a biotech startup. Anyway, he worked for a couple of years being the lead developer for GLUE, and now Tom Robitaille loves GLUE so much and other Python software that he's resigned his long-term position at the Max Planck Institute in Germany and moved back to England, where he is now the lead developer for GLUE. So Chris is still kind of a consultant, but he gets a lot of credit. Chris and Tom, I'm going to show you something about GLUE that's not about visualization, it's about data science and data munging, and I just want to give credit where credit is due right now, because graduate students are the ones who frequently have to combine data sets, and it's like takes a really long time to munge all that data. And so their first idea was, wait a minute, yeah, this is going to do linked view visualization, but it's also going to not make us combine the data sets. It's going to glue the data sets together. So you'll see that glue has a double meaning when we get to that. And that came from the people who otherwise would have had to do extra work saying, wait, we don't want to do that either. And then the other person listed here is someone who several of you know, Michelle Borkin, who's a visualization researcher at Northeastern. She's a professor now. She worked with us from the very beginning of all of this astronomical medicine stuff at Harvard when she was an undergraduate and then a graduate student. But she's still very much involved in the project. Okay, so now let's talk about astronomy for a few minutes and think back to why astronomy was such a favorite of, say, Jim Gray's, who will come up later, in terms of a test bed for data science, okay, and for visualization also. So yes, we can go all the way back to Stonehenge, which is how we can get 3,500 years ago, and say that people have been observing the sky very carefully for that long, at least that long. And then some people see this second picture of Ptolemy here, and they see that tube, and they think, oh yeah, they had telescopes in the year 100. No, actually, they just had these sighting scopes that looked very carefully at the positions of things on the sky. So people have been measuring the positions of astronomical objects for a really long time. So that means we have long time baselines for some objects. And they even built dedicated structures that they called observatories, but they still didn't have any telescopes. They were often in castles. And then it wasn't until Galileo came along that there was this very important transition from just naked eye astronomy to using telescopes, okay, so using instruments. And I'm going to argue in a minute that the internet gave us a very similarly important transition in astronomy, but that one was around 1600. And then shortly after Galileo, so we're talking just 400 years ago, we have what most people would call the scientific revolution, but between 1600 and 1937 here, the only kinds of telescopes were ones that looked at optical light. Okay, they didn't go beyond what you could see with your eyes. They were just an enhanced version of what you could see with your eyes. So the first non-optical telescope was a Grote-Rebert's radio telescope just before World War II. That actually led to the production of many radar systems in World War II. So you see, astronomy is useful, just in case you didn't know. And now I'm going to tell you how it can also save lives. Okay, and then there was another big transition where we went from the ground to space. And so the first satellite space-based observing is this NASA Explorer 7, which was a mission that looked at high-energy radiation that thankfully doesn't get through the atmosphere. Okay, so that's coming up on almost 60 years ago. But then the big deal was with the advent of the internet. What's funny to me is actually people thought that what the internet would be good for in astronomy was controlling telescopes robotically. So it's kind of like I thought, oh yeah, let's make something where we can do link view visualization, et cetera. And I was only concerned about the visualization end, right? But the graduate students were like, no. First we got to glue all the data together, right? So the astronomers who didn't want to stay up all night were like, wait a minute, we can use this thing to control telescopes and we can observe in the daytime when it's nighttime somewhere else, okay? So that's what the robotic telescope idea was, and you could respond very quickly. But it turns out that probably more important is the idea that you can put all the data online and share it and use it to understand the universe. So this screenshot here, oddly enough, is of Worldwide Telescope. I'm just going to assume that everyone at Microsoft Research knows or should know what Worldwide Telescope is. Okay, we'll talk about it a little bit later, but it's a way that you can access almost all the astronomy data that's online through one very beautiful interface, and you can get to much deeper information, including the literature and imagery at all wavelengths. And what I'll show you later is that we've managed to build the web API for Worldwide Telescope directly into GLUE just recently. So GLUE is much more multidisciplinary than astronomy, but it's a good example of how you can put a particular discipline's tools inside of the environment. But Worldwide Telescope came a decade after another project that Curtis worked on with Jim Gray and Alex Lay, which was the Sloan Digital Sky Survey. For those of you who don't know what that is, that was the Sloan Foundation investing a lot of money to do an all-sky survey that would have a dedicated telescope that would just keep looking at many galaxies and imaging the sky. And they're on the 14th data release, and all of the previous data releases are online. And this is the current version. Oh, it says DR14 right there. So this is the current version of the website. Curtis can tell you what the original version looked like. And then you can see over here a slide from Jim Gray, who presumably, I think you all have heard about Jim Gray and his story. But I like this slide because I put here that why it is that people like astronomy data, people in data science in general, and it's because it's very visual, because it's all open, and because it's all worthless, okay? Okay, so there's no economic incentive for people to do anything with astronomy data, unlike, say, biotech data or privacy issues like in medical imaging data. So that's why astronomy, which is kind of a weird niche field, gets all this interest from the data science and visualization community, because we have large and interesting data sets that are free and open. So here now let's talk a little bit about why astronomy and medicine make this perfect combination. And this is just a set of images to give you the idea that frequently what people do is what might get called multimodal imaging, okay? So here you see a galaxy in the optical, a radio version, an X-ray observation, and a composite image of all three things, which, by the way, are primarily made for press releases, okay? People are really most interested in these individually or in very specific combinations that I'll show you. Actually, I'm not sure I'll show you, but they are possible in GLUE, okay? In medical imaging, they do the same thing. But for the visualization researchers here, I'm going to tell you something depressing that I found out very recently. So you see how, first of all, we know rainbow is bad. Okay, we'll just acknowledge that. Okay, forget about that. I didn't do this, right? But you see how there's like this green scale here and a gray scale here, and you might think that it might be useful to do something like this, right? To have a sort of pinkish image and a bluish image and combine them and see color. Medical people hate that. I didn't know this, but they're so worried about inaccuracy that they hate color. And so, as a matter of fact, what they will do is they'll put this kind of color stuff on top of a black and white image to emphasize particular regions. But I'm going to talk later about trying to customize glue to many different communities. And so we add something that we think is fantastic in astronomy, like the ability to composite images. And the medical people were sitting there when we showed it to them and went, we don't want to tell you this, but our colleagues hate that. So we can try to teach them that that's valuable, or we can try to make other arrangements. So on the left here, you see images taken through someone's head that you probably can understand, in that this is slices through someone's brain, you know, imaging slices, not actual slices. I'm pretty sure you're clear on that. And if you're a radiologist, you have such a detailed knowledge of what someone's brain looks like that you can kind of put that back together. And I was talking to Andy Van Dam, who was here the other day, and he was complaining that when he had brain imaging done, that the radiologists were doing this and they were looking, you know, one slice at a time. Why weren't they looking at a 3D image? And the same thing came up, that they're not used to it. That's not what they're used to. That's not what they want to do. And so toward the end of the presentation today, I'll talk about how we might or might not overcome that. But in astronomy, if you do the same thing and you slice, I'm not going to get into, you can ask me later if you want to know how we make 3D images, but let's just say this is essentially a 3D image of a big star-forming region in space. And if I just sort of slide back and forth the same way, for those of you familiar with medical imaging, this is called a grand tour, where you just go back and forth through the data. You don't know what this looks like in 3D, right? It's not a brain. You don't know a priori what it looks like. So we have to do better than that. And I'll show you first, if you look at all the data that contributed to that little bit of data I showed you a minute ago, to put it in context, what this is, again, I'm not going to really talk much about astronomy, but just quickly, the background image is a very old, 100-year-old optical image of a large region of the sky, and then all these colored things are other planes of information you might be interested in. What is important for our discussion right now is the green contours are the sum of all that gray fluff that you saw before. So I'll show you if I superimpose them, okay, and I just slide back and forth, you can imagine that if you summed up all that whitish, grayish fluff, you would get to those green contours, okay? This is still not helpful, right? And so you want to know in a kind of much more visceral way, what does this look like? And so in our first collaboration with medical imaging people, we used the VolView software, which comes off of ITK and BTK. Some of you are probably familiar with that, to see that, in fact, that molecular cloud has all kinds of interesting structures, including, if I can, you see this huge loop here? That is completely not apparent when you look at 2D slices. But the same way, some of you are familiar with Michelle's work on artery visualization, the same way you want a 2D view and a 3D view in order to say if you're going to do surgery, you want a 3D view, but if you're going to do very detailed measurements and analysis, you still want those 2D slices. One of the principles that we kept in mind when we were trying to figure out what to do about building glue was that we wanted to keep both the 3D views and the 2D views linked to each other. So anyway, this is the kind of data that my group in astronomy deals with a lot, where we have information about sources on the sky that are kind of in catalogs. We have big 3D images like that. And then we have all kinds of diagnostic statistical plots that I haven't shown you. Okay? And so boiled down to the simplest way you can think about it, if we pay homage here to John Tukey and what he meant about live linking plots, he didn't think very much about 3D except for 3D point clouds. I'm talking about 3D actual volumetric data. Okay, but either way, you're talking about having 2D views, 3D views, some kind of statistical and abstract plots, and then being able to live link some subsection of those plots that you chose either algorithmically or interactively and see the effect right away. if you have never watched this video, I don't have time to show it to you, but I always put all the slides online. Okay, so this is John Tukey's original video from Stanford when he was at the Linear Accelerator working with the particle physicists who had all this very high dimensional data in the 1970s. And I don't have the picture, but anyway, he designed a device with them to have buttons for rotating and zooming and all this because there was no mouse. And so it's just, if you watch this video and see how much harder it was to do all these things, on the one hand you go, oh my God, I can't believe they did this. And on the other hand you go, oh, it was so much simpler to figure out like what the actually totally important things were because you couldn't do all the other things. And so you had to strip it down to what you possibly could do. Anyway, I highly recommend that video. And I would consider that kind of the origin of these ideas of linked view visualization. The first instantiation of that was Datadesk, which I should tell everybody at Microsoft, if you don't know, was a Mac-only product in the 80s that was actually built by Tukey's graduate students from Cornell, and they still run that company, which still exists and is still great software. It still looks like Mac OS 9, but it works, okay? And then there were a bunch of open source efforts. XGobi, GGobi is built on a grammar of graphics. And then, of course, there's the two big papers, one about Spotfire and one about Polaris. Polaris led to Tableau. And I don't actually know what the academic paper, if there was one, that led to Power BI was. So somebody please tell me later. I should add that to the graph. But anyway, so Glue is different than Power BI or Tableau in the most important way being that it's really designed for 3D and 2D images and arbitrary selection within those images, and that it can glue data sets together. Okay? Otherwise, all of the kind of ASCII table data handling and linking and dashboards is much better in Tableau or Power BI. Okay, that's not really what we're trying to do, but the interactivity is shared, the goal across all of these products. Okay, so this is just a static view. I'm going to show you a couple of videos, but just to familiarize you what the interface of Glue looks like, I'll just look at this for just a minute, and then I'll show you some videos because they go by kind of quickly, and then I will do some live demo. Okay, risky here. Okay, but anyway, no, I mean the program works, but I should just tell you that I don't have enough room for multiple Python installations on my laptop, so I have only the developer version. Okay, so if something bad happens, you should know that the stable version is just fine. Okay, so anyway. Here you are. So it's not, by the way, you know, a lot of us involved in this project don't love the aesthetics of how it looks, and you have to remember that this is meant as software for researchers, okay? This is not meant as some D3 masterpiece, okay? You can output from this to things that look pretty nice, and then you can fix them up in D3, but it's really meant as a very fast, interactive environment, okay? So over here is where you load in data sets, and you'll see in the video, actually, he won't demonstrate. I can demonstrate for you if you want how you glue them together, but there's a special interface for saying, you know, this column or this attribute of this data set is the same as this one, or is related by some function, or is related by some user-defined function, or even a combination of attributes is the same as another one. So you can do that kind of logic on your own. And then once you've set all that up, anything that you choose in any open plot highlights live in the other one. And if you can't make live highlighting, then you can, if you can't make it with just a lasso or a square or a circle or whatever, you can type whatever you want in this IPython console. And I'll show you later, because I'm sure some of you are thinking ahead and you're saying, does this work from inside a notebook? And the answer is sort of at the moment, and there's more coming that has to do with Jupyter Labs. I'll get to that in a minute. Okay. But anyway, so then down here, there's kind of a concept of layers within each plot, and you can control the properties of each one. And again, these are options for those layers. And I think I just will show you the videos now. You don't really need to know what the rest of that says. So let me show you the first very short video, which was made actually a little while ago. And so there's much more than what's in this video. But we'll just start with this, and then I can show you more. I assume you can all see.
Glue is a program for data exploration and visualization that allows users to better understand the relationships that exist within and between data sets. The main interface of Glue provides different data viewers. In this example, the viewer on the left shows an astronomical image of a region where stars are currently forming, and the two viewers on the right show a scattered plot and histogram derived from a separate catalogue of stars in this region. The viewers support interactive selection of data subsets, and selections are automatically propagated to other data viewers. In this example, the selected stars are shown in red in all viewers. One of the main features of GLUE is the ability to link together different datasets using linear or non-linear mapping functions. In this example, we have linked the image and catalog data to make it possible for the stars to be shown on top of the image. Three-dimensional data viewers are also available. In this example, we can see the 3D distribution of all earthquakes recorded around the world in the last 6 years. The points are colored by the depth of the location where the earthquake originated. The lighter colors show earthquakes that occur deeper in the crust. This viewer also supports highlighting of selections made in other viewers, as well as direct 3D selections. GLUE is designed from the ground up to be a multidisciplinary tool and allows users, for example scientists, to develop plugins to support particular data formats or data viewers. This example shows a volume rendering visualization of medical data that consists of braid scans. We have used GLUE to overplot two different datasets, and we can interactively explore this data in 3 dimensions. Finally, GLUE is written in Python and makes it easy to interact with the data and subsets using a built-in IPython terminal. For example, we can define new subsets programmatically and have these be automatically highlighted in the interface.
It's taxi data for New York City. It's actually a very interesting data set. But I just wanted to say one thing, because we were talking, was it just yesterday we were talking about the information visualization and scientific visualization? And so there's this kind of debate. Ben Schneiderman once kind of, well, he didn't quite yell at me, but he disagreed with me when I told him that it was a really important union of information visualization and scientific visualization. And sometimes, at least what I understand, is that people think of scientific visualization as literal representation of scientific data. And this is a very rudimentary set of statistical plots, but we have much more interesting kind of information visualization plots, dendrograms, and things like that that can be built in to GLUE. And it's really the ability to select on both sides of the scientific information visualization divide that gives GLUE a lot of its power. And I'll show you something really weird that is useful when you can think in a very high number of dimensions. And I'm going to spend most of the second part of this talk talking about the challenges that lie in front of us, not just the technological challenges, but getting people who are used to thinking in terms of very specific kinds of plots to think about their data in a more abstract, high-dimensional way. And I'll give you an example right here by showing you a feature that I'm pretty sure only exists in GLUE. We just had this proposal from NSF accepted, and we got the reviews back, and there were 6 reviewers, and we got a bunch of comments saying, yes, this feature is unique. So I used to not be confident about saying things like this, but now at least 6 people who reviewed this say that this feature is unique, what I'm about to show you. So here's a map. I'm just going to control this. So this is a galaxy, okay? And what you're seeing here is, instead of that molecular cloud where I showed you going forward and back, and it's just sort of this mess of stuff, here you can kind of see that there's like spiral arms to this galaxy. It's pretty hard to see what's going on. So if I let this keep going, you're going to use this tool that's a spectral tool, okay? So what that means, let me just pause this here. What that means is, in that pink box, this is show me, if you just sum up all the information in that box as a function of the dimension that's essentially the slider dimension. You can think of it as going into the screen, but it's the slider dimension, okay? So it's like if this was a 3D cube and I was cutting through it, stick a probe that has the size of that pink box through the whole cube, and then show me the distribution of material. So that's what that is. And then you can hit this button that says collapse, and so now you can see the image summed up over all those velocities. That's not unique. There's a lot of software that can do that. This is the unique part. Okay, so then you say, all right, in that range of velocities, I'm interested in these features, okay, which I'm tracing out, and then that trace is going to become a new dimension, okay, in the data set. And so then you can make this plot, which is actually showing you along that red line. The red line would be the x-axis of that plot. What does the emission look like? And so this is useful, yes, for galaxies, but it's useful for other things like arteries and blood flow along arteries. So I'm going to show you mostly astronomical examples today, but you should know that we're working closely, mostly through Michelle, with the people at Mass General and a couple of other hospitals in Boston trying to optimize these features. And so Glue can actually already input a lot of medical imaging formats and GIS data. And I just want to take a few minutes to look at the general architecture of it and then go through all these challenges and do whatever live demo you like. So you mostly should have a handout. I don't know if everybody has one, but I'm just going to show you kind of slowly how this works and what this is like the very base level architecture of Glue, just to show you what we would love. We would love if people would use it, add to it, build custom loaders and custom plot types. And so I'm going to show you what those all are now. Okay, so the icon of Glue is actually pretty useful because it shows you kind of a very stylized version of that Tukey story I was telling you, where you have different kinds of plots, sort of your standard 1D, 2D, and 3D plots, plus some bonus custom plots. This one with dendrograms actually comes with Glue because we use that a lot. Okay, but you can make your own. Okay, and then of course when you highlight anything in any of those plots, it automatically highlights in the other plots. Okay, so that's the linked view Tukey part. Okay, and then the graduate student and postdoc, I don't want to do more work, but this is a brilliant idea part. Okay, is the left-hand side of this, where you might have a bunch of data files that you might otherwise have to combine or rationalize in some way, but instead there's this whole architecture for gluing them together by their shared attributes. And that's, in astronomy, for example, there are coordinate systems that are tied to the galaxy that are called latitude and longitude, galactic latitude and longitude. And there's other coordinate systems that are tied to the Earth and the Sun, right ascension and declination. And there are complicated but well-known geometric transformations between those things. And that's a built-in function in Glue. So if you have the astronomer's version of Glue, you can even glue right ascension to latitude and longitude. You don't have to glue right ascension to right ascension. Okay, so the built-in functions for gluing stuff together is actually pretty good. They're pretty good. Okay, so those are the two reasons for the name Glue, right? And then what comes when you just download the software is a standard set of data loaders, so tables and various kinds of image files from, again, astronomy, medicine, GIS files. I can't remember, there's one or two other things. And then the ability within the package using the GUI, you can define new variables. You can export to D3 with this little package that we made that's very rudimentary called D3PO. It's actually made by some friends of ours. Yes, it's called D3PO, sorry. And then more recently, we added support for Plotly. Both of those need updating, but they should work at a basic level. But they basically just export the kinds of plots that those packages can support, which does not, for example, include volume visualization, not right now. Okay, and then you get the standard plots at one end. And then there's this idea of this whole plugin architecture where you can have custom loaders that you define, okay, and you can add those to your environment and other people can have made them, right? So you can have the GIS Glue environment if you want, and people can have packaged all of that for you in advance. These are just the fields that we've worked in. So again, it's medicine, astronomy, GIS, and whatever else. By the way, we got this weird email relatively early on from Yelp. Apparently data scientists at Yelp. All right, so I really want to put like a Yelp logo here. I don't know exactly what they're using it for, but I love Yelp. And so I consider it a great success that our software is being used at Yelp. But anyway, and you can add, it's a Qt interface for the GUI, and so you can add custom buttons and features. But basically the idea is that over here is input formats and over here is output formats, and you can redo that to your heart's content. Okay, and then the sort of options is you can change this config.py file, which is the user specified settings for data loaders, colors, plot types, etc. By the way, it does use a Brewer color table, but you can screw it up just like anybody can screw up any other software. So I'm sorry if I show you anything ugly. But anyway, right, and then you have access to all the matplotlib functions. It uses what used to be the IPython terminal, now a Jupyter environment. And then from the Jupyter notebook, you can launch Glue from the notebook. What we're going to do is actually integrate Glue into Jupyter Labs. And so we've talked to Fernando Perez. I was at a meeting last fall, where we have in principle a plan to work directly with the Jupyter Notebooks people and make it so they could have many plots at once. For those of you who use IPython Notebook or Jupyter Notebook, you know it's kind of one plot at a time, and that's not really useful for a linked view environment. Anyway, I'll come back to that a little bit later. Okay, and so all of this is at gluviz.org, which is a pretty nicely maintained website, thanks to the fact that Tom Robitaille is incredibly efficient. Okay, so there's your handout. And just to stress again, because a lot of people here are visualization researchers, we are not claiming that any of this is a whole cloth new invention. Okay, the parts that are new in terms of making it useful for people are this linking the data files that have shared attributes. We're pretty sure that Selections doesn't have two eyes, sorry. That you'll see in a minute that you can draw a kind of arbitrary shape, and so you can trace things out, or you can input some kind of algorithm that traces things for you and then adjust it. So being able to do that in an image or in a 3D volume, we don't know of other software that can do that. If there is some, please tell me about it. And then this connection to the Jupyter environment is also unique. All right, so then I was going to go through a little bit of a list of challenges and then do as much live demo as you want. Okay, so the challenges are what I said before about you really want people to understand what these 3 Ds mean. So data, dimensions, and display, right? So you want them to think about the kind of inherent dimensionality in their data. And I don't mean like it's spatial and it's 3D. I mean, I have 17 columns and these columns would be useful next to each other. Or I could visualize, income by apartment floor, by age, by weight as a volumetric graph if I wanted to, okay? In other words, it can be very not spatial and not intuitive, but people just don't think that way. And so in astronomy, people have been really trained to think about 2-dimensional displays and particular standard kinds of plots. And so let's say that this cube actually represents one of these so-called position velocity cubes that I showed you before, because the 3rd dimension in astronomy is actually velocity, but it doesn't matter. So it matters for this example. It shouldn't matter is my whole point, okay? But anyway, people think of that, and velocity, by the way, comes from frequency. So that means that the way that people get the data like that in astronomy is at each one of these positions on the front of a cube, you take a spectrum, and that's intensity as a function of the z-axis, okay, in terms of depth into the screen. So you have some data, but then there are names for how you display it, right? So if you display one of those so-called spectra that I showed you before, just look like kind of like a scraggly Gaussian, that's a cut of intensity along this yellow line. People call that a spectrum or a spectral energy distribution. And it might be that this is a time dimension, and so then they would call that a time series, and they would make some kind of XY graph, right? If they had the front of this cube or any slice through the cube, they would probably call that an image. So kind of like the planes of the 3D cube that I showed you before, or they might add it up like I did when that collapse feature in Glue, and that would still be just an image in the parlance of astronomy. And then in 3D, people sort of understand the idea of 3D renderings, okay, which is a generic thing, at least that's not specific to astronomy. And then these 2D movies, those slice movies, if you think about the medical people, there it's a real obstacle, okay, because they're really used to only those 2D movies and they don't want to think about 3D volumes. And then when it gets really interesting, you're talking about time as another dimension, right? So you're talking about time varying 3D images and interacting with those. And a lot of medical imaging now can superimpose things like blood flow or diffusion on top of the 3D data. And this is really, really powerful, like actually can save people's lives, okay? But it's pretty much only ever used, that kind of imaging, in a research setting, not in a clinical setting. And so there's a huge user interaction, both psychologically and cognitively, psychologically meaning sort of sociologically, challenge. Okay, so this is a joke here. It's not funny to you, it is to me, okay? The bone wars actually has nothing to do with medicine. There are these objects that we uncovered a few years ago in the interstellar medium that are called the bones of the galaxy, okay? And there are these very, very long, skinny things, and that's what I was going to use to do a demo at the end. So I'll come back to this and do some live demo, but just to give you some idea, what we do now, this is the 3rd paper in a series, relies very heavily on using Glue and now even on plugging Worldwide Telescope into Glue. And other groups still haven't completely adopted this way of doing things, even though the software is public and they see us demonstrate and they go, oh. And so they make a lot of shortcuts and they actually make a lot of mistakes, okay, because they make these shortcuts. And that's what's led to this discrepancy between results from different groups. And so this paper here is actually by a graduate student, a fabulous graduate student, Catherine Zucker, who has gone through and sucked down the data from all the other groups who disagree about the nature of these objects and reanalyzed it using a lot of software, including GLUE, and sort of harmonized all of this. And the paper shows the differences between these objects. But that's a very kind of insider astronomy issue, so I'll leave that out for now. And again, this is where you can see the Worldwide Telescope integration. And this kind of messy environment is, you know, I bet a lot of you work with scientists or are scientists, and you know that this sort of messy, not perfect looking, non-dashboardy thing is how people typically work. Okay, so we'll go to the live demo in a minute, but let me just finish what we're trying to do in terms of a broader community. So Dave, this is for you. Okay, so we have an antenna. Here, I'll make the little plane fly because it's so much fun. Okay, I made this slide when I was in Switzerland a couple months ago, and so that's why I just want you to know it's not Alaska Air or something, it's Swiss Air for them. Okay, so this is some trails from airplanes over Boston. And the reason that we have this data is because we were thinking about how to explain GLUE to kind of the general public and possible future investors. And by the way, we sort of are considering making a kind of custom solutions company based on top of GLUE, but we haven't taken the plunge to do that yet. And even if we do that, it'll still be open source, MIT, Python the whole time, or whatever language becomes better, but Python for now. Anyway, so you can buy an antenna and you can receive digital signals from airplanes. So the antenna is about $20. You hook it up to the Raspberry Pi, and then you put it on the roof of a fine observatory at Harvard, and you claim that you have your own radio telescope on the roof of the observatory at Harvard, for which you spent less than $100. And then you can explain to people that you can track three-dimensional positions of all the airplanes, and you can integrate that with, say, weather data, things like that. So we're working on collecting data for that. And just for you, Dave, here's a plot from GLUE showing you the GIS loader with the airplane tracks. And obviously, you can make 3D plots and things like that. And if all of that isn't enough for people, you can make custom viewers. Here's one that was made by somebody that's interested in basketball. My personal favorite is Chris Beaumont, who I told you, the one who now works for Netflix, and he's very funny. He made a visualization of the path through Super Mario, there was some contest about like the most efficient way to win at Super Mario, and there's actually a GLUE data type that is Super Mario. Okay, so I'm not kidding. You can go find it. Anyway, all right, so this is what Jupiter Labs is supposed to look like. I don't think that there's a production version of it yet. That's not what I've seen, so maybe I missed something, but I don't think so. And you can see here, though, that there are many graphs at once. And so the idea is you can have your notebook and your sort of glue-like environment over here, and this would let us essentially run large glue-like things on the web. Because right now this is a purely desktop environment. But if we had, Python through Jupiter Labs, then we don't have to rewrite the program, and we can have it much more easily shareable. So speaking of sharing, the proposal that was just funded by NSF includes a collaboration with the Concord Consortium, who's a group that does educational technology, a very good group in Concord, Massachusetts. And they have this product, that they've made called Kodak, which stands for Common Online Data Analysis Platform. And it's intended for grades 6 through 14, so kind of, beginning college all the way back to 6th grade. And it has a lot of glue-like features, and it looks a little shinier than glue. And the idea is to see if we can come up with a sort of data science curriculum for that age group, which apparently there's a real need for such things. And so the proposal that we had funded isn't to actually do that, it's to make a prototype to do that and then propose in the future to do that. So anyway, that will be hopefully coming soon. A big one that I bet a lot of you have already wondered about is how big a data set can GLUE handle right now. And it's essentially limited by the memory of your laptop, which can be very taxing for your laptop, but is good enough for most of the applications, especially in the medical world. It's fine. Their data sets are actually pretty small. When it's not fine is something that we want to do next with glue. So imagine that instead of having one patient and you're looking at their brain scan and trying to analyze blood flow and whatever in their heart or their brain, imagine you have 1,000 patients. Okay, you have data for 1,000 patients, and now your dimensions include like patient number. Okay, and you actually want to be able to do operations across lots of patients at the same time. So forget it. Okay, your laptop will not do that. And so we're trying to figure out how to make a data abstraction layer separate from glue but connected to glue that would let it do things like what Power BI or Tableau already do, which is connect pretty seamlessly to remote databases. If anybody is particularly interested in talking about that, I'd be happy to know more, because we are just trying to figure out how to do that. The Matplotlib viewer, once you get over about 100,000 points, gets kind of slow. And so Tom has actually already put in, for the 2D plots, I think, some data shaders that replace the individual points. And then we have tested, actually, an OpenGL-backed 3D viewer for the point clouds. So we sort of know how to do part of this, but we don't really know how to do the data abstraction layer. We just try. Okay. And then the biggest, hardest one that we do not know how to solve, but we think that augmented reality or some combination of virtual reality and augmented reality might solve it, is how to do 3D selection, right? So some of you have thought about this, so you know what the problem is, and some of you may not have thought about it, but think about 2D selection where I can trace out any arbitrary shape, right? How do you do that in 3D? It's really hard. And so the way people do that in the medical imaging world is to do it one layer at a time, and they make this lasso tracing of things. And people, to do one set of the major arteries in the human hearts, they have these rooms full of technicians at the hospitals, and it takes them 3.5 hours to trace out the outside of somebody's arteries. And you might say, good computer scientists that I know some of you are, not that some of you are good, just some of you are computer scientists. Anyway, you might say, well, why not do that in some automatic, surface finding way? And the answer is the images are really crappy a lot of the time, and trying to just look for a threshold doesn't work. Okay, but you could look for a threshold, or we're actually interested in using segmentations that have been done by radiologists as an input to, say, a machine learning kind of smart selection tool, and then let people just adjust rather than having to select something completely, say, with their hands while using a HoloLens. So there's sort of all these ideas going on, and we do own a HoloLens, but as you see here, mostly what people do for medical imaging is they have a holographic medical image, and then they're just manipulating it and looking at it. They're not actually interacting with it, because the resolution for tracking your fingertips in that device, anyway, is not there. I'm excited to see what this Oasis device can do. But anyway, we think that some integration of a headset and your actual hands, maybe holding a scalpel, maybe holding some kind of touch device, is going to be the right answer. But this will open up a whole new regime in medical image segmentation if somebody can solve this. Okay, so that is the biggest problem. Okay, so that's the end of the slides, and now we can play. But before I start playing, are there any questions or things that you particularly want me to show in Glue here? Yes.
So one of the things I'm interested in is the actual gluing aspect. So data sets are dirty. If you're lucky, it comes with a data dictionary, but a lot of times it doesn't.
Right.
So it seems like a lot of the gluing process is about discovering the mess in your data, interpreting what a column actually means, and what does it mean in this data set versus that data set. So can you talk a little bit about what that workflow is like of sort of?
Sure. I mean, here's something that has a bunch of data files open, but I can open more, or I can make a new tab. But let me just show you. I'll just move these things out of the way for the moment. So let's say I have loaded in these data sets. I don't know if you can see on the left, but you probably can't read them, but each one of these is an individual data set. You don't have to glue them when you open them. So you can just bring them into the program and then sort of mess around with them. So if I go here and I select a table viewer, then I don't know how big that is. Okay, so I can just open up a straight table of that file. And what did I do? Sorry. Okay. And so here you would just see the column headings that the people have already given you in the table. But you can't, in other words, we don't have any data manipulation in the GUI. In the IPython terminal, you could poke at the data and see what you want. But then let's say that you like the data, then there's a separate interface for gluing the data, okay? And so right now, you can see the links that have already been made. Down here, this list shows you the current links, but I can just re-glue something that's already been glued. So if I take 2 of these data sets and I select them here, so let's take that one and that one, and I say galactic latitude is the same thing as galactic latitude, and I say glue, it's just making a redundant link that's already there. But so it's that easy, and then I can also unglue things, and then I can also open this thing that says advanced linking, and so these are predefined astronomy functions are in here. But if all of that is no good, then another answer to your question is here. If I say define new component, then I can use all of the existing components to put whatever Python expression I want here using a sort of standard formalism that's explained down there. Just any NumPy function basically will work. So it's not really an answer to your question, but in other words, if you sort of know what you want to do, you can do it within the program, but it doesn't solve the fully messy data problem. Yeah.
I'm a little surprised actually that when I connect things, it doesn't give me some kind of feedback about how many, like in a join, like how much commonality is there versus how much is missing on one side versus the other. So like, it seems if I did a glue that was kind of a dumb glue where things don't actually match up, I'd want to know that.
That's a good point. I'm trying to think what would happen if you did that. Probably the plots would fail, but I don't think that you get an error message. You can, in other words, there are ways that, so if I do this and I say like, I want a histogram, okay, and then I can look, whoa, that's very weird. Okay, because it's doing a histogram of name. Okay, so let's say I do a histogram of velocity, which makes a lot more sense. And so then you can see that I have the black selection and this tiny little purple selection, and I could recalibrate the y-axis. But in any case, I can look at the different data sets and sort of use the visualization to poke around at the properties of the data. And then, let's say these are bad, right? Just like in Data Desk or Tableau, I can go and I can highlight this and I can make that a new selection. And then I can say, I don't want that. I can cut those data out. I can leave them out of the plots. I can flag them. So you can kind of interactively look at one data set at a time before you decide to glue them. So you see that just made a new selection, and I can use that in all the other plots. And you can rename them, and each one can have a different color and different properties for the different data sets that you have open. And also, if it doesn't make sense, so in other words, let's say that 3 data sets have, frog as a column, okay, and then the 4th one doesn't, you can't glue that one, and that one just won't be live if you make some selection that has something to do with frog. But making a stupid selection and then getting an error for it is a good idea. I think right now it just fails, it just doesn't do anything. Somebody else had a question over here. Yeah.
Just relating to that last comment you're making about looking for the magic 3D trace.
Yes.
I'm personally cynical that adding 3D glasses will help. In the end, it's that your fingertip is a 1D thing and you're trying to do a 3D trace, which is a whole lot harder than a 2D trace.
Yeah, we don't want to do it with your fingertip, but go ahead. Yeah.
Right. Well, whatever, a scalpel, still, it's a 1D tip. But you might want to check out Microsoft Research Cambridge's project called Inner Eye, which is meant to solve this specific problem, although in the case of cancer.
Okay.
So it's built for a doctor to, they look at the 3D stack, they do some traces on some of it, and the system interpolates to figure out what the rule that they used was.
That would be great. That would be absolutely great. Is that the...
That's Antonio.
Yeah. I got in touch with Antonio a couple of years ago because Curtis told me about this, and he didn't write back.
He's starting a new business.
So, yeah, he might be busy. So if you can put me in touch with other people in Cambridge.
A large literature on segmentation of medical images. Like there's techniques that are atlas-based, so if you know you're looking for something that looks kind of like a heart,
Right.
there's an atlas of heart, of typical heart shapes, and that can help a lot with that.
Right. So the people we're working with on that are at the Martinos Center. So Bruce Rosen is the head of this Martinos Center for Medical Imaging, and they have a few actually more than a few data and segmentation experts on staff. And so things like that where we want to look for a whole heart or something, that's great. And we know about the brain atlas and the heart one, and then there's this whole human thing. And the challenge that we're trying to solve is a little bit, that we should implement for sure, and we will. But you know how in Tableau and things like that, you can bring in polygon boundaries that are the boundaries of known counties or known states or something like that. What we want is the thing you can do in Yelp, actually, where I want restaurants in this lasso. You know, you can just do anything. And so in the medical imaging world, the problem is like a tumor might have the characteristics of a lot of other tumors, but it's not in a place that an atlas can define. And so that's why we're looking for, and this thing from Microsoft Cambridge labs might be good, but a kind of informed smart selection tool that is informed by things like those atlases and other segmentations of the same kind of imaging. But you're right that we should explicitly build in some of those atlases, so we could do that.
I think Antonio at NRI is doing a lot of machine learning on really large data sets that helps them define soft tissue boundaries, which is, I think, a little bit different than Kellogg.
So what else would you guys like to see where?
So
Yeah.
you mentioned like your ability to trace out the arms of the galaxy and then
Right.
project onto that. It reminds me of colonoscopy visualizations I've seen. I don't know the details of it, but I've seen projects where you get a 3D medical scan of someone's colon, and then there's some way to find a path through the center of the colon, and then they produce a rectified image. So that,
Okay.
that's the closest thing I can think of.
That's good. We should look.
Also sent you an email about a transmogrifier.
Sorry, I can't hear.
Transmogrifier.
Transmogrifier.
Anyway, I'll just send it to you. It's just 2D, but they trace and pass in an image, and then they actually deform it. And they have a cool animation. I thought perhaps that would be useful for you to help convey how the image is transformed into that.
Oh, that would be great.
Yeah. So
That would be
I
great.
sent you the link because it's impossible to remember the name.
I might. That's very strange. That's helpful.
So it's straightening rivers, since you're going to compare the lengths of the string.
Yeah. No, that actually would be great for this long, skinny filaments project. I actually had left open, it was in Chrome. I had left open Worldwide Telescope running in the browser so that I could show you what these things look like if you wanted to see, but I'm not sure you can see. Can you see this long, skinny black smudge? Okay. It turns out that those things can help you define the structure of the galaxy. Okay. And so we have done a lot of work to try to find a bunch of them. And so this is actually a tour in Worldwide Telescope that we made a few years ago as a kind of introductory level of this project, where we just kind of went along the plane of the galaxy and by eye, found all of the things. I'm just going to slide through the tour one thing at a time. Found all the things that look vaguely like that. And then there's been a lot of follow-up with all those other kinds of data sets that I showed you in the talk and in Glue to see whether the three-dimensional positions of these things make sense and how they compare with simulations and things like this. But we still don't have a good way to kind of unwrap them and see whether they're the same if you kind of untangled them. So it would be really interesting to try that. So, by the way, for those of you who don't know, Worldwide Telescope now runs really well in HTML5. And so this is the web version. It's even playing a tour. Too bad Jonathan's not here to bask in the glow. Anyway, so it's 10:59. I promised to be done by 11, but I'm happy to take another question if there is one. Oh. All right, well, thank you.